Newton's law of cooling is given by this first-order linear differential equation, where K is a constant, T is the temperature of the metal, and A is the temperature of the surrounding environment. As the functions of x are constant values, the rate of cooling is dependent on its current temperature and not the amount of time passed. We see this in real life when metals and other materials cool rapidly when their temperature is significantly higher than the surroundings. However, as the temperature drops, their cooling rate slows down, independent of the time elapsed. As shown from the slope field of the equation of Newton's law of cooling, where A equals 3 and K equals 0.3, the temperature of the objects approaches the surrounding temperature, which we observe when metals are left to cool after being reshaped/forged. Increasing the K value to zero point 0.8, we observe that the gradient lines become more steep, meaning that they approach the surrounding temperatures at a different rate. Different metals conduct and emit heat at different rates, and by finding the different K values of these metals, their ability to radiate heat can be compared. Furthermore, by separating variables on both sides and integrating them, we can model a function of temperature in terms of time utilizing Newton's law of cooling in the form of an exponential decay function. This blue slope field represents the differential equation of Newton's law, while by finding the values of K, A, and B, and inputting the temperature of a metal body at different times into the exponential equation, a specific function for the temperature of a metal with respect to time can be found. A represents the surrounding temperature and the temperature that the metal approaches, while K determines the steepness of the gradient lines. An increase in K makes the lines more steep, increasing the rate of change of the temperature towards the surrounding temperature. B, meanwhile, is determined by substituting the temperature of the metal at certain times, and an increase in B increases the temperature of the metal at different times as well as the rate of cooling with respect to time. However, the rate of cooling with respect to the temperature still remains the same. Newton's law of cooling is very useful for practical applications such as measuring the temperature of a heated metal. For example, a blacksmith may use Newton's law of cooling to consider the time it takes for the metal to reach a certain temperature, which is useful as different metal temperatures may be required to reshape them.
Created using Powtoon.